There's this powerful, invisible force that courses through our electrical grid every single second of every day. It's called electrical resonance. Now, this thing can be just a harmless background hum, or it can be this catastrophic tremor that literally shatters the systems that power our entire world. So, how on earth does that work?
So, let me ask you this. What could an opera singer shattering a glass possibly have in common with a massive power grid failure? I know, it sounds like a weird riddle, right? But think about it. The singer hits that perfect note, the glass starts to vibrate, and then boom, it shatters. In the same way, a power grid gets this sudden surge and transformers can literally explode. The answer? The thing that connects them? It's just one word: resonance.
Okay, so to really get our heads around this, let's go back to something simple. Picture pushing a kid on a swing. You know how it works, right? You don't just shove them whenever. No, you push at that exact right moment, right at the peak of their backswing. And with every single one of those perfectly timed pushes, they go higher and higher and higher. That perfect timing, that's everything. Okay, now let's swap out the swing for our electrical grid. And those pushes, imagine they're tiny little electrical vibrations. Well, when those pushes happen to hit the grid's own natural frequency, its own perfect timing, the energy doesn't just add up. Oh no, it multiplies. It amplifies like crazy to levels that are, well, they can be unbelievably destructive. So what's really going on inside the wires? I mean, how does good, clean power all of a sudden go bad? To figure that one out, we've got to dig a little deeper, get into the technical stuff, and see exactly why engineers work so hard to stop this from ever happening. All right, so at its core, every electrical system has these two opposing forces, kind of like a tug of war. You've got inductance on one side. Just think of that as the system's inertia. It's resistance to any change in the flow of electricity. It's the heavy stuff, like big motors. Then on the other side, you've got capacitance, which is all about the system's ability to store energy, like you'd find in long power cables. Now, usually, these two are pulling against each other, and that keeps everything stable. But at one very specific frequency, what we call the resonant frequency, they perfectly cancel each other out. The tug of war stops, and when that happens, there is absolutely nothing left to hold the energy back. It just surges. And let me tell you, this surge isn't a one-size-fits-all problem. It comes in two, let's call them particularly nasty flavors. First, you've got parallel resonance. This is what causes dangerously high voltage. Think of it like the water pressure in a pipe suddenly going through the roof. It's going to burst everything connected to it. Then you've got series resonance. This one creates dangerously high current. Now this is like that same pipe, but instead of pressure, it's the sheer volume of water becoming a raging river, just melting components from the raw power. Either way, it's absolutely disastrous.
And look, this is not just some textbook theory. The consequences are incredibly real. We're talking about transformers overheating and just failing. Breakers and fuses that keep tripping for no apparent reason, leading to those super frustrating power outages. Resonance also messes up the overall power quality, making it dirty. And it can even trick the measurement tools, which is really scary. It means the people watching the grid might not even see the disaster coming until it's way too late.
So you're probably asking, okay, what's actually causing all this? And the answer is, well, it's fascinating and kind of ironic. A lot of the time, it's the very technology we're installing to make our grid more modern and efficient that's accidentally setting the stage for resonance. Here's how it usually happens, and it almost always starts with good intentions. Let's say a big factory installs some power-saving capacitor banks. Great. Then they add a bunch of modern equipment like variable frequency drives for their motors, or maybe just a whole new office floor packed with computers. The thing is, these modern devices, they don't draw power in a nice, smooth way. They create this kind of electrical noise. Engineers call it harmonics. And if the frequency of that noise just happens to line up with the grid's own natural frequency, well, you know what happens next. The swing starts getting pushed, higher and higher. But thankfully, this isn't a hopeless situation. Engineers have a whole toolkit ready to fight back and, tame this electrical beast. It's this constant battle of detection, prevention, and correction. And honestly, it's the only thing that keeps our grid from literally shaking itself apart. The main game plans really fall into a few key areas. First up, for prevention, engineers use something called detuned reactors. All these do is basically change the grid's natural rhythm so those pushes are offbeat and don't line up anymore. For fixing problems in real time, they've got active harmonic filters. These are pretty cool. They work just like noise-canceling headphones for the grid. They listen for the bad noise and create an opposite signal to just cancel it out.
And in really high-tech or electrically dirty places, they use things like static VAR generators, which clean up the power without adding any new parts that could cause resonance themselves. Of course, the best tool of all is doing system studies before building anything to design a resonance-free grid from the start.
At the end of the day, you can just think of all this tech as a set of really sophisticated shock absorbers for the grid. Their whole job is to smooth out the bumps and vibrations on our electrical highway, making sure a little tremor doesn't turn into a full-blown destructive earthquake. Okay, so we've gone through a lot of the technical stuff, but why does any of this actually matter to you? Simple. Because this incredibly complex balancing act is happening right now, behind the scenes, 24/7, just to keep our entire modern world switched on. Think about it. Every single time you flip on a light, charge your phone, or even think about the hospitals and data centers we all rely on, you're placing a bet that engineers have already won this invisible battle for the day. Managing resonance is what keeps our gadgets from getting fried, and it ensures the power grid doesn't just work, it works reliably. And all of this brings us to one last really crucial question. You see, as we add more and more electric cars, more solar panels, and all kinds of complex new electronics to the system, we're fundamentally changing the grid's natural rhythm. So as we build this brand new electric world, are we actually engineering a smarter, more resilient grid, or are we accidentally creating a more fragile one that's tuned so finely that it's right on the brink of collapse? That is the high wire act that engineers are walking every single day.